Jai Hind everyone, my name is Amrita Bhatnagar. I am from CSE department of AKGEC. Today I am going to explain topic deadlock. These are the main outlines of the lecture. First one is system model. Second, deadlock characterization. Third, methods of handling deadlocks. Fourth, deadlock prevention. Third, deadlock avoidance. Next is deadlock reduction, and next is recovery from deadlock. Okay. So firstly, we will understand what is the meaning of deadlock. Introduction to deadlock. How we can understand deadlock. A set of blocked processes, each holding a resource and waiting to acquire a resource held by another process in the set. This phenomena is known as a deadlock. For example, we have two tape drives, which are the two resources in a system, and P1 and P2 are two processes which hold each tape drive but require or send request to another for the another tape drive. You can see in this diagram easily. You can see here these are the two processes, process 1 and process 2, and these are two resources, resource 1 and resource 2. In this case, you can see here process 1 have a resource 1, but it is required another resource 2. But this resource 2 is acquired by the process 2, but it is waiting for the resource 1. Okay, so that both of the process cannot start because of lack of resources. When process 1 gets both resources, resource 1 and resource 2, then it will start execution. But when process 2 will get resource 1 and resource 2, then it will get started. So both of the process are in the deadlock situation because they cannot proceed because of the lack of resources. This is the phenomenon of deadlock, which is very harmful for our system. Right? Now, system model. What is the meaning of system model? We have different type of resources like R1, R2, R3, R4, RM. We have seen here. You can see the CPU cycle, memory space, IO devices. All are the different type of resources which is allocated to the process, different processes, and each resource have different number of instances. For example, printer is one of the resource in our system, and if we have more than one printers in our system, then we can say it has more than one instances of the printer. Now, next is each process utilizes resources as follows. We have three states of the resources. First is the request, when process requests for a resource, and second one, it will get the resource and process will use the resources, and third state is release state where process release the state, process will release the resource. Fine. Now, deadlock characterization. Deadlock characterization means these are the necessary conditions for the deadlock. If this condition holds, then there is a surety of deadlock. First one is mutual exclusion. Only one process can use a resource at a time. It means we don't have shareable resources here. So one process can resource a resource at a time. Second one is hold and wait. A process holding at least one resource is waiting to acquire additional resources held by other processes. Fine. These type of process cannot start their execution because they don't have sufficient resources, but they have hold some resources. They are not releasing the resources and waiting for other resources. That's why they cannot start their execution. No preemption is another condition for the deadlock. If we don't have preemption in our system, then a resource can be released voluntarily by the process. The process can hold their resources up to the long time. That is a very difficult situation in the system. Next is circular wait. Circular wait means there is just a set of process P0, P1 up to Pn of waiting process such that P0 is waiting for a resource that is held by P1 and P1 is waiting for a resource that is held by P1. And in this way, if there is a circular queue in the system, so that each process is waiting for the another process. So nobody is ready to release the resources. That's why they are holding the resources. Some resources are holding, and some resources are they are waiting for the some resources. That's why they no process can start their execution. This is the condition of circular wait. So these are the main necessary condition for the deadlock. If these condition holds in our system, then deadlock can be occur in our system. Resource allocation graph. Now we will understand what is the meaning of resource allocation graph. This is a graph where we have set of vertices and set of edges. V is a partition into two types. V is our vertices, and we have two different type of vertices. First for the process, and another one for the resource. P is for the processes, set of processes, and R for the set of resource. You can see here, P1, P2, Pn are the set of processes, and R1, R2 up to Rm are the set of resources. And next is request edge. This is the request edge. You can see the direct edge from the P1 to resource R. If particular process is requesting for a resource, then we can show is like this by the help of request edge, like this. Assignment edge. Assignment edge is that edge where when the resource process get the resource, acquire the resource, then we can show it like this assignment edge. You can see here P is having Rj resource. That's why we have here assignment edge. So these are the two different type of edges to show the requested assignment of the resources to the processes. You can see here. So in the resource allocation graph, processes are denoted by a circle. First one is, this is the denotation for the process. Second is a resource type with 4 instances. We have this square for the resource to show the resources. And if we have more than one resource, this type of source we have more than one, then we can show it like this by the circle or by the square, small square in the square. So you can see here, this we have 4 instances of square, 4 instances of this resource. So we have 4 squares here. Now next is the PI request instance of Rj. You can see here process PI is requesting for the resource here. So that's why there is a arrow edge from P to resource. And next is the when PI is holding an instance of Rj, then the arrow is from the resource to process. So this is known as a assignment edge, because now resource is assigned to the process. Now example of resource allocation graph. You can see here in this diagram we have 3 processes and 4 resources. P1 have R2 resource and P1 requesting for the R1. P2 have R1 resource, but it is requesting for the R3. It is also have R2 resource, one instance of the R2 resource, and P3 have R3 resource. And here we have R4 resources, which have 3 instances. So this is the example of resource allocation graph. Now with the help, how we can find out deadlocks in the resource by the help of resource allocation graph. Okay, so we have to check the cycles in the resource allocation graph. If we found a particular cycle in the resource allocation graph, then we can say here that there can be a condition of deadlock. You can see here, this is the next example. You can see resource allocation with a deadlock. Now you can see when we have P3 is again requesting for the R2 resources, which is not allocated to P1 and P2 in this time, and this P3 is requesting for R2 resources. Then you can see here there we have a cycle. You can see here P3 is requesting for the R2. R2 is one instance of R2 is assigned to P2, and P2 is requesting for R3, but R3 is assigned to the P3. So again we have a cycle. So there is a possibility of deadlock here. but that is not a necessary condition. If we have a cycle in the resource allocation graph, then this is necessary that deadlock will occur. There is a possibility of deadlock only. You can see here, next you can see here, this is a resource allocation graph with a cycle, but we don't have deadlock here. Why we don't have deadlock here? You can see here, uh, process P1, P2, P3 and P4. We have 4 processes and 2 resources R1 and R2, which have more than one instances. Fine. R2, one instance of the R2 is assigned to the P1, and P1 is requesting for the R1, and R1 is assigned to the P2. One instance is assigned to the P2, and one instance is assigned to the P3. Fine. Now, P3 is requesting for the R2 again, and P4 is one instance of R2 is assigned to the P4. Fine. But we do, here there is a cycle between these processes, but we don't have deadlock here because we have a P4 process which have sufficient resources. Okay, it needs only one resource R2, and if it gets this R2 resource, then it will complete its process and release the resource R2. And when P4 release the resource R2, then P3 will get the resource R2. Then this cycle will break up, and because the now arrow will be from this side to this side. So okay, so that when the P4 will complete this execution, then it will release the resources and the cycle will break. So that's why this is not a case of deadlock. So we can say that every time there is a not possibility that deadlock will occur if the cycle is in the resource allocation. Now, what is the case where we can say deadlock will occur or deadlock will not occur? So that you can see here. If a graph contains no cycle, if we don't have cycle in the graph, it means no deadlock here. But if a graph contains a cycle, then there can be 2 conditions here. If only one instance per resource type, then deadlock. Fine. We should understand that if the sources have only one instance and also have cycle in the resource allocation graph, then the 100% of chances of deadlock. But if several instances are available in the resource type, then there can be a deadlock, but not a surety of the deadlock. Fine. So we have to understand this concept. We have to remember these points. When we have more than one instance, then it means there can be a possibility of deadlock only. Now we can see method of we have understand now what is the meaning of deadlock, why deadlocks occurs. Because of lack of resources, deadlocks occurs. So if we handle the resources very efficiently, then there is a less possibility of deadlock. Now we see how we can handle deadlocks. Ensure that system will never enter a deadlock state. First condition is system should not come into the deadlock state. That can be a prevention. Okay. Next is allow the system to enter the deadlock state and then recover. Next is possibility, allow the system to deadlock state and then we will recover the deadlock. This is another possibility. Third is ignore the problem and pretend that deadlock never occur in the system. Fine. So many of the operating system follow this policy and they don't do anything for deadlock prevention or avoidance. Fine. Because they think that this never occur or if it occur in the months and years. So that is there is no need to handle these deadlock problems. If we restart a system, again system will be work fine. Now, methods of handling, we have first one, deadlock ignorance, where we don't do anything, we don't write any code for the deadlock because we think that it's never occur, or if occur, rarely occur. It is very rarely occur. Second is deadlock prevention. Third one is deadlock avoidance, and fourth one is deadlock recovery. Recovery means when the deadlock occur in the system, we will recover it. And deadlock prevention and avoidance are the policies where we avoid or prevent the deadlock in the system. So firstly, we will see what is the meaning of deadlock prevention. In the deadlock prevention, the necessary condition can be, we will false the necessary condition of the deadlock. For example, we have 4 conditions for the deadlock: mutual exclusion. So in this case, we will eliminate mutual exclusion. What is the meaning of eliminate mutual exclusion? It means we will make our resources shareable. If the resources will be shareable, more than one processes at a time can share shared resources, then there is a less possibility of the deadlock. The first condition is eliminate mutual exclusion. Second is eliminate hold and wait. Hold and wait means now we eliminate that situation where a process holds some will hold some resources and wait for another resource. There must be guarantee that whenever a process requests a resource, it does not hold any other resource. Fine. And require process to request be allocated and its resources before it begins execution, or allow process to request resources only when the process has done. Fine. And last one is, but what happen if we allocated all the resources to the process, then we will start execution, then there will be a low resource utilization, because only one resource will have all the resources, then all process will wait for these resources, then starvation can be possible. So, but this is not a good policy for it. Fine. But we will try here to eliminate hold and wait condition. Now, eliminate no preemption. If we have if we have preemption policy, then we can preempt the particular process, and we can release the resources, so that we can remove the condition of the deadlock here. Fine. So in this case, we will try to eliminate no preemption condition. If a process that is holding some resource requests another resource that cannot be immediately allocated to it, the process must wait. Then all resources currently being held or released. Preempted resources are added to the list of resources for which the process is waiting. Process will restart it only when it can regain its old resources and the new ones it is requesting. Fine. So then in this case, we are trying to preempt the resources so that there should not be any deadlock. If preemption will possible here, then it means the resources can release their resources forcefully, so that it can be assigned to another processes. So that's why we can try to eliminate no preemption condition. Next is eliminate circular wait. Circular wait is another condition for the deadlock. So in this case, we will eliminate circular wait by imposing the ordering in the resource type in the increasing order. For example, if we assign the ordering to the resources, so if the third resource is requested by the particular process, then first and second resource cannot be requested by the another process. So there should be a ordering in the resources, so that it can eliminate circular wait. Now, so these are the 4 points for the prevention. By this method, we can prevent deadlock. We are trying here to prevent deadlock with by falsing these condition which is required for the deadlock. And the next is deadlock avoidance. In deadlock avoidance, the request for any resource will be granted if the resulting state of the system does not cause a deadlock in the system. The state of the system will continuously be checked for safe and unsafe state. In the case of deadlock avoidance, we will divide our system into 2 states, safe and unsafe. If the system in the safe state, it means deadlock will not occur. And if the system in the unsafe state, means deadlock can be occur. So we will avoid to come into the unsafe state. If we assign a particular resource to the process, then we will check after allocating the resource, the system will be safe state or unsafe state. If the unsafe state, then we will not assign the resource to that process. So this is the concept of deadlock avoidance. So we will assign the we will find out the a safe sequence, or we can say that we will assign the resources by checking the safe or unsafe state, so that we can find out a safe sequence for assigning the resources. Fine. Simplest and most useful model requires that each process declare maximum number of resources of each type that it is required or it is needed. The deadlock avoidance algorithm dynamically examines a resource allocation state to ensure that there can never be a circular wait condition. Right? Resource allocation state is defined by the number of available and allocated resources and the maximum demands of the processes. So this is this way we can find out deadlock avoidance. Safe state. What is the meaning of safe state? When a process requests an available resource, system must decide if immediately allocation leave the system in a safe state. So if we assign a resource to a particular process, we will check the state. If it is in the safe state, then it is okay. But if it is not in the safe state, then we will not assign the resource to the particular process. System is in safe state if there exists a safe sequence of all processes. So there will be a safe sequence in the all process. So we will find out the safe sequences in the process. Sequence P1, P2, Pn is safe if for each Pi the resource that Pi can still request can be satisfied by currently available resources plus resources held by all the Pj with j is less than 1. If Pi resources needs are not immediately available, then Pi can wait until all Pj have finished. When Pj is finished, Pi can obtain needed resources, execute, return allocated resources and terminate. Right? When Pi terminates, Pi plus 1 and can obtain its needed resources and so on. So this way we can find out the safe sequences in the processes. So then if the sequence is safe, then we will allow to allocate the resources to the processes. So these are some basic facts here. If a system is in safe state, it means no deadlock. If system is in unsafe state, it means possibility of deadlock. And what is the meaning avoidance? Ensure that system will never enter an unsafe state. So how we can avoid the particular deadlock? By the help of safe and unsafe state. If the system is not in the unsafe state, then we can avoid the deadlock. You can see here, we have divided our states into two types of states. First one is safe and another one is unsafe state. If the unsafe state is there, it means deadlock can be possible here. Now, resource allocation graph. We have a process which is known as a claim age process, which avoid the deadlock. In the claim age, we will indicate that process Pj may request resource Rj and represented by a dashed line. Claim age converts to request H when process requests a resource. When a resource is released by a process, assignment H converts to a claim H. Resources must claimed a priori in the system. It means we will predict that a particular process can demand this resource, so that by the help of claim H we can show with the help of dash line we can show this claim H. You can see this whether it is an example. You can see here. Here in this case P1 have allocated R1 resources and P2 is requesting for the R1. But you can see here there is another resource R2. P1 is not requesting here R2. This is the claim age between the R2 and P1 by the help of dashed line. P1 can claim or we can request the R2 in future. That's why we have this dash age or claim age here. In this way, P2 also can claim for the R2 resources. So these are the two claim age. And if this particular process actually requests for the this resources, then what happened? Then this claim age will be converted in the request age, and then request age, if the resource is allocated to the resource to the process, then this request age can be converted into the assignment age. You can see here firstly P2 is claiming for the R2, then P2 requests for the R2, then R2 will be assigned to the P2. Okay, so this is the but we can, by the help of this claim age, we can find out this is the unsafe state. By the resource allocation graph, we can find out this is the unsafe state, because when we assign the R2 to the P2, then P1 also can request for the R2, and if the P1 can request for the R2, then we will have a cycle here. And what is the meaning of cycle? A cycle means we can have deadlock here, and then the system can be in the unsafe state. So that by the help of claim age, we can find out system is in the safe state or another or the unsafe state. So to find out the safe and unsafe state, we can use Banker's algorithm also. Now, deadlock detection and recovery. This process is used when the deadlock occur in our system, and how we can recover this deadlock. The OS does not use any mechanism to avoid or prevent deadlock in this approach. As a result, the system predicts that deadlock will occur. When we don't have any policies for the deadlock prevention and avoidance, then we have deadlock obviously, and then after the deadlock we will find out the recovery, how can we can recover our system from the deadlock. The OS periodically scans the system for any deadlock in the order to avoid them. If any deadlocks are discovered, the OS will attempt to restore the system using several ways. The OS primary responsibility is to detect deadlocks with the help of resource allocation graph or wait for graph. The OS can detect the deadlock. If cycle forms in a system with single instance resource type, then there will be undoubtedly there will be possibility of deadlock. Deducting a cycle on the other hand is insufficient in the resource allocation graph, which I have already told you. You can see here deadlock detection. How can we find out deadlock will occur or not? If the single instance is there, then detection on cycle means we have there is a 100% possibility of the deadlock. But if we have multiple instance, then detection or cycle is not a good algorithm for find out the detection of the deadlock. So we will use safety algorithm like Banker's algorithm or claim age algorithm. We will use to find out the deadlock. So to find out or detection the deadlock, we will use Banker's algorithm and safety algorithms. Okay. If we have only single instance, then we can find out with the help of resource allocation graph or detect the cycle. Now, resource allocation graph and wait for graph. You can see here I have already explained you what is the resource allocation graph. In the resource allocation graph, we have some processes and resources, and by the help of request and assignment edges, we can draw this graph. And now this resource allocation graph can be converted into wait for graph, where we remove the resources here. We are showing only the process, which process is waiting for which process, and this is known as a wait for graph. From this resource allocation graph, we can drive this wait for graph. In this graph, you can see only processes are visible. We are not having here resources, so that we can see there which processes is waiting for which process, or this can be shown by the wait for graph. Fine. Now, how we can recover our deadlock? There is a first possibility is process termination or kill a process. First one is we can if there is a deadlock, we can kill any process. But we should understand what are the main policies for the kill a process. If we want to kill the process, then we should understand which process we have to kill. We should consider priority of the process, how long the process has been computed, and how much longer to complete. If a process is completed 90%, then we cannot kill it, because this is a wastage of resources of the computer. Fine. So if the process is 10% completed, then this process is terminated, then there will be less loss. How many resources the process has used, how many resources the process needs to complete. So, okay. So these are the points which we should remember when we going to kill a process. And another method is kill all processes. So this is not a good strategy to kill all the processes, but when a situation is very extremely serious, then we can use this policy also for deadlock recovery. Thank you. So today I have explained deadlock in a very easy method. I think This will help you very good manner. Thank you.